Welcome to this session about effect systems. Just before we start, there's going to be a sponsored talk right after the technical paper. So at 5:30, when all the talks are done, there's going to be one more talk that's not in the program from our sponsor. All right, and with that, I pass the word to Magnus Madsen, who's giving the first talk on Boolean unification.
Okay, hello. Nice to see you all. So there's been many talks today about type systems, effect systems. We also heard about inference. But something we don't hear too much about is the performance of type inference, perhaps because it's not always a problem. But in this work, I'll talk about how it became a problem for us working with Boolean unification. So this is a joint work with Jaco and Troels. So I work on the Flix programming language. So it's a functional, imperative, and logic programming language. And in Flix, we can write pure functions. It looks something like this, saying here the addition function, adding x and y, doesn't have any side effects. We can also write impure functions, in this case, say hello. So this function prints to the console and it has an I/O effect. We can write functions that are effect polymorphic. So that's functions where whether the result of applying the function has an effect depends on its function argument. So for example, if you have map and you apply it with a pure function, then that application is pure. If you apply it with an effectful function, well, then it has that effect. Now, a bit more interesting and specific to this work is that if we have function composition, so if I have two functions, f and g, I want to compose them to get a new function, well, then we get the combination of their effects. And so in Flix, the way we express the language of effects is as Boolean formulas. So actually, you can think of pure as being true, I/O as being false, and then EF1 and EF2, well, that's just a conjunction. Okay, so this was already presented at OOPSLA during COVID. Again, the brief idea is Boolean formulas is the language of effects. And so we would like to have complete inference, and we have that using Boolean unification. So that's nice. We implemented it, and it's working. But as we've been extending the library since then, actually tripling its size, the compiler was getting slower and slower. And so if you're building like a real system, it's really frustrating to see when performance is just falling off all the time. And so we needed to do something, and that's what this talk is about. So let's first look a little bit at what is Boolean unification. So in the Flix standard library, actually, somewhere deep inside type inference, this constraint arises. So here we want to unify x and y and z with x and w. Now, if you look at this equation, I'm sure you can find solutions. For example, if we set all the variables to true, that's a solution. Another solution is we could set all the variables to false. We could also be more sophisticated and see it's actually okay if we set just x to false. Then we can choose the rest freely. In fact, it seems there are many solutions. We could also set y to w or z to w and can come up with many solutions. So normally this can be a challenge for type inference because, which solution should we choose? Now, fortunately, in the case of Boolean unification, there is a best one, if you will, or a most general one. And this substitution captures all of the other substitutions. So it captures all the other solutions. In this case, it's this one, this substitution here. Okay, good. So if I have such a Boolean unification query, I want to unify this side or that side, well, how do I do it? So actually, this problem has been studied for a long time. So there are two algorithms, go back more than 100 years. One is Boole's algorithm, and the other is Löwenheim's method. Boole's algorithm is also called SVE, for successive variable elimination. And it's not too hard to see that Boolean unification is a generalization of set, if one of the sides was true, for example. So Boolean unification is a computationally hard problem. Okay. So in general, we're not going to be able to solve it efficiently in the complexity sense. Now the problem is, if we run Boole's algorithm on the previous query, this is the solution we get. Now it's the same solution, or rather it is equally most general to the other solution. The other solution was this small one down here. So we can obtain one from the other via substitution. But unfortunately, if you just implement the algorithm and run it, this is what we get. Now, what happens in type inference is that you're not solving one unification problem, you're solving a series of unification problems. So you solve one problem, and now you have the substitution, you apply it, and then you have to solve more Boolean unification problems, and now these formulas completely get out of control. And so this is the root cause of performance degrading. Okay, so in the original paper, what did we do about this? Well, the library wasn't as big, so we just had some ad hoc rules, like x and true can be rewritten to x and x can be rewritten to x, and so on. But now the library is much larger, and we have more richer effects. We have regions, for example, user-defined effects. So this doesn't work anymore. And if we try to type check the library with what we had back then, even with a very large computer, taking a lunch break, it doesn't terminate. Okay, so what do we do? Well, we need a line of attack. And so the idea is that, hey, let's look at these queries that arise during type inference and see if we can learn some information about their structure. And then if there's some structure, well, maybe we can exploit that and choose better data structures or algorithms. But of course, no matter what we do, problem remains NP hard. So we will be looking at heuristics. So we considered several resource questions. I'll not go into a lot of detail, but just first of all, how many variables are actually in the queries? Do queries repeat? So there's good reason to believe they repeat because many functions sort of treat effects in similar ways. And is there any structure to the queries? So as a test subject, we use the Flix standard library. So this library, I think, is quite large for a library that's subject to an effect system. At least we have like 35,000 lines of code, 3,000 functions. There's a whole data log solver written in it, which includes a JIT and sort of data log optimizations. So we run the Flix compiler on the standard library, plus a large suite of test cases, and then we record all the queries we see. And we see queries at 2 times, during type inference and later during minimization. So in total, we recorded about 50,000 queries, and we find that most queries involve very few variables. Now this actually makes sense because we usually have variables when we have higher order functions. So for example, list append, well, that doesn't have any effect variables. List.map would have one effect variable, and so on. So if you think about how code is written, usually functions are not, in general, that higher order. Moreover, we find that many queries repeat. So in fact, that we only see 380 syntactically unique queries, and of those, only 89 are semantically unique. So this number is kind of like, you can think of it as how many different ways are effects used throughout the standard library. Okay, so given this knowledge, what can we do? So we came up with a sequence of strategies as follows. So the first strategy is just the original baseline from the paper. Then the second strategy is that, well, we know there are a few variables in play. So we actually pre-compute a table that for every Boolean formula of 4 variables or less tells us its minimal representation. So you give me some large Boolean formula, but if it has 3 variables, I can compute its function profile and look it up in the table and get a minimal representation. Then we take the table and we add caching. So if we've seen the query before, then we just use that answer. And finally, we add something even faster than caching. We hard-code a few special cases that repeat a lot. So this is kind of what we're doing sort of in the years after, and I would call this sort of we have to do something, it doesn't work, so let's keep adding a lot of hacks and see if we can get it to work, right? Then at some point, it's like, okay, maybe we need to go for heavier technology. So let's switch to binary decision diagrams. So this is an efficient way of representing Boolean formulas. But then there's this issue that we have a very large compiler, and so we can't really, BDDs have a tendency to be infectious, but we can't really keep BDDs throughout the compiler, so we still need a way to get a minimal representation and then translate it back into an explicit form. And so here we did something naive. Then on top of that, we add this QMC algorithm. So that's a heuristic for we can use to turn BDDs back into small formulas. Then on top of that, we add back the caches, add back the special cases. And then the last strategy, we have everything where if the query involves 4 variables or less, then we use the tabling. Otherwise, we use BDDs. Okay, so these are kind of the results in one slide. So this is the throughput of the compiler. The first strategy doesn't work, so there's no column at all. And for the other strategy, we can see that as we go up sort of down the strategies, performance improves. In particular, we can see the strategy 7, the kitchen sink, if you will, is the one that achieves the best performance. And that's because we're doing software engineering here, right? So we've now designed an implementation that really squeezes out as much performance as possible. And so with strategy 7, we are able to reduce the overhead spent down to 7%. So of the total compilation time, we only spend 7% on Boolean unification. Just briefly, so the tabling, I think I explained it already, but the idea is to pre-compute a table that for every formula with less than 4 variables has its minimal representation, and then you ship that with the compiler. We can compress it down to this. And then we use that table to look up in. And here you can see that, well, it was 95 as we saw on the previous slide. This is the distribution of queries and how many variables they have. So there's really just a long tail of a few queries that have many variables. Most of the queries have very few, even 0. That's like true and false, pure and impure functions. Okay, so that explains why tabling works. So what about caching? Why does caching work? So this graph here shows the ratio of unique queries. So we see for queries with few variables, we see them many, many, many times. So it makes sense to cache them. Whereas, for example, there's just one single query with 7 variables, so we only see it once. So caching wouldn't really help us there. Okay, so putting all this together, this is kind of an overview of the algorithm. So we get a Boolean unification problem like this. We look at how many variables there are. Less than 4, less than equal 4, we look in the syntactic cache. If it's not in the cache, then we run this Boole's algorithm, SVE, and where we use tabling to keep the formula small, and that gives us the unifying substitution. If there are more than 4 variables, then we're in kind of one of these tail cases that are much more complex to handle. Then we look in a BDD cache we have, and then we run SVE with BDDs if it's not in the cache, and then we have the unifying substitution. Okay, so that was a lot of stuff, right? If you're building your own compiler, what would be the takeaway from this? So a few lessons we learned, I would say. So first of all, if you do Boolean unification and you think you can simplify the formulas by hand, I don't think that will work. You need more sophisticated technology. Second, switching to BDDs actually made everything tractable again, but there's a very high overhead. And so we speculate that this is because BDD libraries, and we tried, I think, 4, they are very much optimized for big problems. So think like n queens or something like this, right? So for example, one BDD library would start n threads per query. But of course, starting 32 threads is kind of expensive when you're just solving a very small thing. So BDD libraries do make it tractable, and we find this PJ BDD to be the best one. There's a paper about it too. But then going further than the BDDs to really get a significant increase in performance, we exploit the fact that queries are simple and have few variables, so that allow us to have special cases, caching, and to use tabling. And so sort of in summary, the idea is we have this hybrid approach where based on how many variables there are, we will use one or the other strategy. So here at the end, a few questions that I invite everyone to consider is, could we maybe use different variable orderings in SVE to compute smaller unifiers? So without going into details, this is not about the BDD variable ordering, which is kind of a well-known thing that's been studied. This is about the ordering that is used inside the Boolean unification algorithm. There's another ordering you can choose there, and it has a huge impact on performance, but it's impossible for me currently to predict which one is better. The other thing is sometimes we actually know several of the queries up front, so could we solve them in a different order and increase performance? Right now, interestingly, it's like the syntax-directed order works best. So kind of descending into the AST and then starting from the roots and up. And finally, all of this has been done for Boolean formulas, but what about other Boolean algebras, for example, set formulas? So if you're interested in these things, come help make Boolean unification fast. So in summary, Flix is a functional imperative logic programming language. We have a Hindley-Milner type system. We have an effect system in there. Effects are modeled as Boolean formulas. I showed you very briefly, pure functions are true, impure functions have I/O, but it's actually a bit richer than that explained in the paper because we also have region effects, and they are modeled as these rigid variables. We use Boolean unification. The way we got it to work and scale is that we switched from things that were completely ad hoc to modern technology, so BDDs, but also then we added a lot of extra infrastructure just to catch the common cases and make them really fast. And also we have empirical evidence that sort of each addition actually gives you some performance. And that's it. Thank you for your attention.
Please, if you want to ask a question, step up to the microphones on either side of the room.
So I was wondering, have you considered the ergonomics of the effect system with Boolean some Boolean operations. So I mean, so there are some optimization of the Boolean unification, but is there any guarantee? Well, for example, they infer a simple effect type for the term, or is there any metric to show which one is more simple?
Right. So that's a good question. That's a good point. So I talked about performance because you want the compiler to be fast, but also you don't want the user to hover over an expression and then they are told this is the effect of that expression. So that's a big usability concern also, and the reason we want to have kind of minimal representations.
Hi, thanks for the talk. I guess one question is, you mentioned that I guess initially you need like even with 512 gigabytes and a long lunch break, you couldn't compile the standard library.
Yeah.
So with these changes, how long and how much memory do you need? Can you compile it in like 5 minutes, or is it still several hours?
So compiling the standard library, and you need test cases because otherwise it's dead code and it's eliminated. So 35,000 lines of standard library plus 30,000 lines of test cases, so 65,000 lines of code can be compiled in like 1 minute.
Oh, okay, that's cool. And also, is it, you mentioned that the underlying problem is NP hard. Is it the case that like you're fully exploring that NP hard problem, or is it, is the encoding actually some subset that might be easier?
No, it's not a subset. You can, I mean, if you take one step and you have this substitution, and so you get all the connectives and you have to, but I think it may answer a slightly different question. I think in type systems and programs, we have the hypothesis that types will be small. So for example, even for ordinary Hindley-Milner, it's possible to write this counterexample with this lead ladder and the types become exponential. And for effects, it's also the case in Flix that there are small effect formulas. So the problem is computing them.
Right.
Your turn?
I think I might have just figured out the answer to my question by sitting in this line, but just to be sure, when you say you pre-compute the result for up to 4 variables, if the same variable appears multiple times, it counts several times, right?
No, it just counts once.
Okay, then aren't there infinitely many 4-variable Boolean formulas?
Yes, there are. But you take any formula, it could be very long, right? But if you consider the truth table of it, it only has at most 4 variables. Then you can find the rightmost column by evaluating it for all valuations, but there are only at most 4 variables. And so you take that column, right, and that's the index into the table. And there you find the minimal pre-computed representation.
Okay, let's thank the speaker.